Recording. Okay, so let's get started. There was a leftover question from Monday, which was about operating the CRC circuit. I didn't have built at the time, now I've built it. And that lab, I think, was one of these. Let's try 7B. I think it was the last part of 7B, if I'm thinking of it right. Yes, so here was the circuit, the CRC circuit. It had 4 data latches. This is not a real CRC. The word size would be bigger. And there might be more excluded ORs. But we have 4 flip-flops or 4 data latches. They are edge driven, so they have a clock. The output of one flip-flop feeds into the next flip-flop. That makes it a shift register. But it has these additional excluded ORs. So that's what's turning it into a CRC, a cyclic redundancy check. So this outgoing output, this sort of last output, comes back around and is fed in as one input of an excluded OR in this very last flip-flop, and in this case, in the very first flip-flop. Okay. So what I want to see, I want to maybe jack the magnification up a little bit, page width. And I want to see this data that I'm going to put in. And then I want, okay. Need this to be a little lower. Okay. So I built the circuit. I have a switch for the data and a switch for the clock. They can be high red and low black. The clock feeds into the clock of all of my flip-flops, so they are sort of synchronized. I have the excluded OR going into the first flip-flop and going into the last flip-flop, and the Q feeds into the D, the Q feeds into the D. The Q is feeding in through the D, but this time through an excluded OR. The other input of the excluded OR is the output of this output that's sort of on its way out of the shift register. I have a probe on the Qs to see my result. I haven't done anything with the set. I haven't done anything with the reset. I haven't done anything with the Q tildes. It's all the Qs, it's all the Ds, the Qs, and the clocks. And when you're building this, make sure you grab an excluded OR in the list under TTL. Sorry, let me go I usually go to Miss Digital, TTL, and the excluded NOR is in the list before the excluded OR, but we want an excluded OR. So that's just a common mistake. Okay, so we have this circuit now built. It is a memory circuit, so it has a history dependence. And so when I give you this problem from scratch, I am assuming that you have just turned on the CRC. So I'm just going to start the simulation. So I'm supposing that it has no history before this, and but the history is important, so you will not turn the simulation off during the time of this operation to see what's happening. Okay, so I'm going to turn it on and begin the problem. I encounter the first 1 in my data, and so 1 corresponds to high for us. So, and this is the data I'm going to put in, so I make the data switch high. And then I'm going to go, this is data coming through in serial. So a CRC check is something you do when data is being transferred in serial. And so I'm going to go through a clock cycle. So I'm going to type a C. I'm going to move the C up and down to make sure that I've seen both edges of the clock. So I've gone through a full clock cycle. In a binary system, a clock is something that is low, then high, then low, then high, then low, then high. It just goes from one state to the other state. And a full cycle is a low and a high. So if I say move a clock through a cycle, it means change its state and change its state back. So that was this first one. Now the next data is also one. So I'm going to keep the D switch high. And then I'm going to move the clock through another cycle. So I'm going to type C up and down. So now I've moved through 2 clock cycles. I set the D too high to correspond to the 1, and I went through the first clock cycle up and down. I went through the second clock cycle up and down. Now I'm going to go next to this third bit, which is a 0, and then there are 1, 2, 3, 4, 5 zeros in a row. Okay, so I'm going to set the D. The D is moving to 0, so I'm going to flip the D switch. And then I'm going to go through 5 clock cycles. So that's 1, it's always an up and a down. That was 1, 2, 3, 4, 5. That was 5 clock cycles to get here. Now I'm at this 1 down here. So I'm going to make the data high and go through a clock cycle. Then the data is low. So I'm going to change the data and go through a clock cycle. I'm going to make the data high and go through a clock cycle. So D high, go through a clock cycle, and then make the D low and go through a clock cycle. And then I get an output from my CRC. Okay, so I'm sending the data in, and I sort of am doing this in parallel. I have a regular old shift register where I'm bringing in my actual data. And then I have this shift register with the excluded ORs, and it's doing this error checking for me. And so the result of this process on that data gave me 1010. Now, the idea of error detection is that if there was an error in the data, you would get a different result. And then you would, if that error were to have occurred, you will notice it. So there will be there's a sender. We're talking about some kind of transmission of data. There is a sender and a receiver, and the sender does some kind of calculation like this, some CRC calculation. The receiver does some CRC calculation, and then they compare results. And if they differ in their results, then it is presumed that an error occurred. Well, we know an error must have occurred. And then we cannot find the error. We don't know what the error was. We just know that an error occurred. And since it's a transmission process, the receiver will just say to the sender, something went wrong, send that again. What I got was there was a mistake in what I got, send it again. Okay, so that is the operation of the CRC. Let's do just one of these. I need to change one of the bits. So I had so many zeros in a row, I got bored. So I'm going to put, when I change it, my choice will be to change one of those zeros. So let me just change this middle one so I don't get so bored. Okay. And the idea here is if one of those bits got flipped somewhere along the way, then I should be able to detect that by getting a different answer. So let's see. So I'm going to turn it on. So it's starting fresh. And I'm going to make the data high to start and go through a clock cycle. And I'm going through a second clock cycle with the data high. And then the data is low. And I'm going to go through a clock cycle. I'm going to keep the data low and go through another clock cycle. Then the data goes high. And I go through a clock cycle. Then the data is low. And I go through 2 clock cycles. 1, 2. And then the data is high, and then low, and then high, and then low. And each one there's a clock cycle. So data high, data high, clock cycle. Data low, clock cycle. Data high, clock cycle. Data low, clock cycle. And I get a different answer. Before I got high, low, high, low. Now I'm getting low, high, a different result. So this would be, in this process, a detectable error. And that's the idea. With an error detection scheme, you want, now you can just play a pure probability game in that our CRC output has 4 bits. And so there are, in 4 bits, 2 to the 4 possible states. So that's 16 possible states, and only one of them is correct for the data. And so you could say, I am, I'm going to find, if an error occurs, I'm going to find it 15/16% of the time. So it's possible that I would get the same for some pattern of 1s and 0s. I might get this original pattern and not detect my error. But if I have an error, if it's just purely random error, I should find it 15 out of 16 times. So that's somewhere in the 90s, right? So let me do it. Calculator. Just standard 15 divided by 16. So 93, almost 94% of the time, with the 4-bit CRC, I should find a mistake. Oh, somebody's talking to me. Why is that an error? Because we are presuming that this is the data I sent. And then in the original, so I am just saying, here is the data, this is the right data. So then if I change something, then that makes it an error. It's not an error in all cases, but in my scenario, this is my desired information to be sent. This is what came through. It's clearly not the same, so it is an error. And then the question then is, do I detect that error? So I have some data, which is, I just made it up, but it is the data that I'm deciding that I want to transmit. And then I am on purpose making some error in the data and then asking myself, if that was the mistake that occurred, would I catch it? It's an error detection scheme. So the question is, would I find that mistake? And so we've argued that, okay, this mistake that we have in B, we purposely made a mistake, purposely got this red one wrong, and I got a different answer here, 0101. And so it's a different result from the original, so I would detect that mistake. Okay, so again, I am presuming that there is a mistake, and then the question is, do I find it? And I would find that mistake. Okay. Now, CRC is supposed to be, like if it's a random error, then it only depends on how many bits there are in the answer. So anything you did that produced a 4-bit answer, if it's like totally, if you're getting all possible answers equally likely, then you would find, as we said, if there were an error, we would find it 15 out of 16 times, or about 94% of the time. But the real engineering comes in to find the process that finds non-random errors. What are the kind of errors that are likely to occur, and what schemes find those? And there's a type of error known as a burst error, where you get sort of not just some random bit along the way or 2 random bits along the way, but bits that are sort of together wrong. And that's known as a burst error. And CRC is designed, like you do studies and you pick where to put these excluded ORs, and you put them in the best place to detect the mistake. Okay, but that is the game. So what are you responsible for in the lab? To build this circuit and to operate it. And what are you responsible on the test? To have this circuit already built. Please have it already built. And then to operate it. I will give you a string of data, and you will pump through the process, and you will give me an answer, and you'll give me a screen capture showing me that you actually operated the circuit. You didn't find some CRC calculator out on the web. God knows everything exists out there on the web, so you could probably find some CRC calculating thing somewhere. I don't know, I haven't looked. I don't care, I know how to do it. I don't need a calculator. But I will ask for a screen capture showing the results so that you can't just cheat me and get all the points. All right, any questions? And even if you get it wrong, if you've built a circuit, then you should show me that you do some screen capture and get points for making a screen capture of the thing, even if you sort of say, I never get this right. But if you built a circuit, there are points just for having the circuit. And then you slap down some 0s and 1s, and you know, look, you got a 94% chance of getting it wrong, but maybe you'll get it right. You never know. Maybe you're lucky. Questions? Okay, so that is, you know, almost always a question on test 2. All right. So what else was there in Unit 7 I have to tell you about? One of the big topics is floating point numbers. I have to tell you about floating point numbers. And one will be how to go from like regular sort of decimally expressed numbers into floating point numbers. Let me turn the simulation off. And the other one will be, if I give you a floating point number, how to get the sort of decimal version. Okay, so let me do my crazy Word document kind of approach here. I already have a Word document. Let me just make a new one. Okay. So we have played with what's called fixed point representation. So we said, let's say that there were 8 bits for the whole number and 8 bits for the fraction. Then we could say, what is 16.17 in fixed point representation? So I could then say play this game, programmer, and I could say, what is a 16? Oh, it's, I have 8 bits, so it's 0001, 0000. Okay, so 0001, 0000. So that was a 16. And then to do this fractional part, we say there are 8 bits. So I'm going to go over to scientific and say, if you remember, the process for getting the fraction was to repeatedly multiply by 2. And if I have 8 bits, I'm going to multiply by 2 8 times. And so I'm very impatient, and I just shortcut that by multiplying my fraction times 2 to the 8. Multiplying by 2 8 times is multiplying by 2 to the 8. So I'm going to say 0.17 times 2 raised to the 8. And then I'm going to take the whole number part. Some people will round. This affects the last bit. Some people will round. I usually just truncate. So I'm going to take this 43, and then I'm going to go over to programmer, and I'm going to do a control V and paste that 43 in. And then here is my binary. Again, I'm looking for 8 bits. So it's point, I lost it. Let me copy, and then I can paste. Saves me having to remember things I can't remember. That's not where that little break is. That's where the little break is. Okay. Now, did this make sense? 0, 0? Yes. After the dot, we have negative powers of 2. That makes this the halves place, this the quarters place, this the eighths place. And this fraction we're trying to represent is less than a half, so 0. It's less than a quarter, so 0, but it's more than an eighth. So we get a 1 in the eighths place, and then the rest. Okay, so that is fixed point representation. We say I want how many bits for the whole number and how many bits for the fraction, and that is that game. And then we say questions like, what's the biggest number we can represent? What's the smallest number we can represent? We play that sort of a game to see, okay, I've used so many bits for the whole number, so many bits for the fraction. What answers can I come up with? And then, so you have some range. The more bits you use, the bigger range. Now, the bits you use for the whole number kind of tell you how big the numbers can get, whereas the number of bits you use for the fraction tell you sort of what your precision is. How small of changes in numbers can you deal with? Okay, because you're never going to get exactly 0.17. Only if you have a fraction whose denominator is like an exact power of 2 can you represent it exactly. And this 0.17 is 17/100ths. The denominator is not a power of 2. 100 is not a power of 2. And so you're never going to represent this exactly. That's why I had to throw something away. I had to truncate. And even if I had more and more bits, I'd get closer, but I would never get it exactly. Okay, so I never have exact precision. But the more bits I have, the more precision I have. So the whole number part in a fixed, the whole number side tells me how big the numbers can be. And the number for the fraction tells me what kind of precision I can have. And then it's limited by the number of bits. So now let's think about what we do when we want really big numbers or really small numbers, or let's go back to decimal. We always think about it in decimal first because that's what we're more used to. And then we say, how do we turn that over to binary? So if you have really big numbers to deal with, you do with what's called scientific notation. So let me take some number. I'm just typing randomly here. Okay, so I have some number and and that's a fairly large number. I want to represent that in scientific notation. I take this number and first I do something trivial. I'm going to multiply it by 10 raised to the 0. 10 to the 0 is 1, so I multiply it by a number by 1, so that does absolutely nothing. And I don't want to do anything to the number other than write it a different way. And the next thing I'm going to do is I'm going to move this point 1 over, and I'm going to change this to a 1, and that's the same number. I have divided the whole number by 10. I've taken the power of 10 and raised it 1, and so that's the same number. And I just keep playing this game in scientific notation. And I'm going to move it now. Again, I told you before that I'm very impatient. So the rule in scientific notation is the dot should be here. So I have 1, 2, 3, 4, 5, 6 more places to move it. So every time I move the decimal place, I have to add to the power. And I already did it once, but I have another 1, 2, 3, 4, 5, 6 to go. So I'm going to do that and add my 6 to my 1 and get 7. And so now I have the scientific notation. And that is a decimal idea that we use when we have to represent very large and very small numbers. It allows us to deal with numbers that are quite big. And if these powers are negative, to deal with numbers that are quite small. And then I have two dots, which is crazy. Okay. And then, okay, with the numbers big, we're going to maybe take some of this away. So when the numbers are small, we're going to allow them to have, a hundredths place or something like that. But if the number gets to be big, if it's like Avogadro's number from chemistry or something like that, we don't care about hundredths. We don't even care about tens or hundredths. The number's so big, we care about, what's the power of 10 to the 22 or 3 or whatever the hell it is. And okay. So here's our idea, and we want to put it into binary, put in the binary version. Okay. So in the binary version, so because this number, the way it is now and fixed up here, this 16.7, we're kind of wasting these leading zeros. We had to have them if it's 8 for 8 places for the whole number and 8 places for the fraction, these leading zeros are kind of like wasted. And I could use them over here to have more precision. And that's sort of the game that we're going to do in scientific notation. So we're going to play the same rules as scientific notation. The dot comes, we have a power. 10 was our base in decimal, but now our base is going to be 2. And we're going to have a dot, and the dot goes after the first non-zero digit. So here it was 7.59. So we put the dot, there's a single digit, a single non-zero digit, then the dot, then more digits, and then times 10 raised to some power. That's scientific notation. Now we're going to put it over into binary language. So we're going to put the dot that we have here, this dot gets moved here. So that's 1, 2, 3, 4 places. To move that dot 4 places, we would have to multiply by 2 to the 4. So let me come back to this example. Scroll down a bit. And now if I want to move this dot here so that the first non-zero dot is the first non-zero digit and then the dot. So forget those. That's what we're trying to get rid of. Here is the dot now, and the dot moved 4 places. And so I multiply by 2 raised to the 4. Okay, so this is the new game. This is just the same game as scientific notation, but adapted to binary. Okay. Now we have here a power of 2, and we have here some number that multiplies that. Okay. Now, one difference between binary and decimal in this game is here in scientific notation, this can be anything other than 0. It can be 1, it can be 2, it can be 3, up to 9. Down here in binary, it has to be, the rule is the first digit has to be a non-zero digit. And in binary, there are only 2 digits, 1 and 0. So if it's a non-zero digit, it's a 1. So it always starts with a 1. And so when they play this game in floating point notation, we're not quite in floating point notation, but we're working toward it. But because this digit is always a 1, one of the rules to get to full floating point notation or rules is we don't need to represent the 1. We don't need to store the 1 because it's always 1. Don't need to store that first digit. It's always 1. Okay. So that 1, we need to bring it back. When we store, we throw it away. And then when we want to work with it, we bring it back. So that 1's going to there are times we're going to have to say, okay, it's time to get rid of the 1. And then there are times where we're going to have to say, okay, it's time to bring back the 1. Okay. Then we need how many bits are going to be after the dot. And our answer is 23. 23 digits after the dot. Sometimes I'll be talking about 24 because I'll be including this 1. And then, but when we store, we'll take it away. So storing, there are 23 digits after the dot, and those get stored. Those get stored. So the first digit, it's always a 1. We don't store it. So sometimes we're taking it away. Sometimes we're adding it back in. The 20, we pick for floating point 23 digits that we're going to keep after the dot, and we're going to store all of those. Okay. That is known typically as the mantissa. So that's just a vocabulary. That's called the mantissa. Okay. Now, if the number was greater than 1, then that power is of 2. 2 raised to a power is positive. And but if the number started off less than 1, then the power of 2 might be negative. So the power of 2 may be positive or negative. And so we have to deal with representing positive powers and negative powers. And we played this game before, and previously our solution was the 2's complement. And that's not the answer this time. Why is it not the answer? I don't know. Go back and find the engineers who came up with this in the 1970s or whatever it was and ask them. I don't know the answer to that, why they didn't use 2's complement. They didn't. They used something called biasing. Okay. So it's going to be an 8-bit. We're going to use 8 bits for this power. We're going to use 8 bits for the power. Okay. Now, if I normally had 8 bits, what is that? That's 200. That's 2 to the 8th, or 256 things. Now, when I asked you about FAT 12 on the test, I wanted the answer 2 to 12. I wanted some just fast counting problem about bits. And then what did some of you do? Of course, you Googled it, and there's certain reserved things that weren't used to address clusters. And so you got some slightly smaller answer, which is a correct answer. So I didn't take off points, but you sort of, I don't know, missed the point if in my mind. But anyway, okay. So there are 8 bits we're going to use to represent this power. That means that there are 2 to the 8 possibilities. That's 256. So what would I normally say? I would normally say I'm going, if I were playing the 2's complement game, I would say I'm going from minus 128 to 127 if using 2's complement. It's going to be similar, but what we do with biasing is we add 127. There are certain things reserved, and so you don't get to the minus 128, so it's more 120 minus 127. And when we call it bias, so bias means add 127 before storing. So I have some negative power of 2. I'm going to add 127 to it. And that's going to give me a positive number. And that positive number is what I'm going to store. Okay. And this is known as the exponent. So we talk about the exponent, the mantissa, and the exponent. There's one more part. The overall number might be positive or negative. So there's a power that could be positive or negative, and we handle that by bias. The overall number might be positive or negative, and we just have a simple sign bit. So there's an overall sign, and which is handled by a sign bit. The sign bit is 0 if the number's positive, and 1 for negative. Okay. And what do you do? So you get some range of numbers from this, which is a much broader range of numbers than you get. So altogether, this was 23 and 23 and 8, 23 for the mantissa, 8 for the exponent, 1 for the sign bit. Overall, that's 32. So I'm using 32 bits, and I'm getting a bigger range, bigger numbers and smaller numbers than I would if I took my 32 bits and broke them up somehow into some fixed point representation. That's the purpose of floating point numbers. It's the same as the purpose of scientific notation, be able to have very big numbers and very small numbers that come up in science. If the numbers for floating point aren't big enough or small enough for you, what do you do? You're going to go work for NASA. They have very big numbers or small numbers. The floating point range isn't quite enough for you. What do you do? Floating point is a type of number that you declared in programs. What's another kind of number that gives you a bigger range? Say again, a double. So a double will take more bits than 32 and play the same game. They will say, okay, here's how many for the power. Here's how many for the mantissa. And they'll just, they will get a bigger range by just using more bits. That's what we mean when we say a double. Okay, so let's play this game, okay? Trying to make sure I didn't get any, I'm not missing any chats. I don't think I missed any chat. Okay, so let's play this game. Let's pick a number. Let me save this. Where am I at? Documents is good enough. Say floating. Okay. Let me make a new page, insert page break. Okay. So I'm going to pick some number. I will start with a 0. All right, there's some number dot, there's some other number. Okay, that's my number I want to represent. Let's make it negative for fun. Okay. All right, so let's see what we would do to represent this number. So first we would say the sign bit, that's easy, is 1. So I give you this problem, there's going to be a problem like this, probably one problem in the go from decimal to floating, and probably another problem where you go from floating to the decimal number. So there's probably 2 of these on test 2. And the easiest point is the sign bit. You're running out of time. I'm saying turn it in, turn it in, turn it in. Put down the sign bit. If it's negative, it's a 1. If it's positive, it's a 0. Easiest points on the test, get them. Okay. So now let's start thinking first about fixed and then changing it from fixed to floating. So let me start with my whole number, 90988. So I'm going to be here in programmer mode. I'm going to clear out. I'm going to put in 90988. And here is the binary. And I'm going to copy that. And so I'm going to say 90988 goes in binary to here. 90988. So I don't have to do any funny minus sign stuff. I'm done with the minus sign. Sign bit was 1. Done with the sign. Don't talk about it anymore. Okay. Now I want to know how many bits I used up for my whole number. These are in groups of 4. 1, 2, 3, 4 groups of 4, and 1 more. Is that 17, 4, 8, 12, 16, 17? 17 bits. Okay. how many bits did I say were in my mantissa? And I have two possible answers to that, depending. I'm not ready to store yet. So I need to keep, at this stage, I am keeping the 1. And then I'm going to, when it comes time to write down the final answer, I'm going to say, okay, throw away that 1. But for now, I'm keeping it. And so I have 24 bits. And I'll say, including the 1 I will not store. And I have used 17. Right? I always use however many bits I need to represent the whole number, because that's more important to me than the fraction. Right? You always pick on the poor fraction. If somebody's going to not get enough bits, it's going to be the fraction. And fractions are pigs for bits anyway. You never, only very special fractions can be represented exactly anyway. So the whole number is bigger, so we care about it more. And you never satisfy the fraction anyway. So I have 24 bits to use. I'm doing floating point. I'm not doing double. So I have 24 bits. I've used 17. That means I have 7 remaining. Right? I can't spell remaining. When you do this, it's all hidden from me. So if you need to use the calculator to say 24 minus 17, that's fine by me. I don't care. I'd rather you get it right than you do it in your head and make some mistake. Okay, so there's 7 bits remaining for the fraction. Then we play our fraction game. 0.0917 times 2 raised to the number of bits, which is 7. And what do we get? Put myself over in scientific mode. 0.0917 times 2 raised to the 7th. That is 11. This thing, copy, paste. I'm going to truncate, so it's just 11. Some people will round. I don't care about that very last bit, or sometimes because of the rounding, that last bit can affect other bits. I don't care too much about the bits at the end. If I see it looks right in the beginning, then if you decide to round rather than truncate, I'll say fine and good. I tend to truncate. Okay, so then I go back to programmer and I take the 11 and it is represented by 1011. 1101. Probably could have done that one in my head. I should have been. Okay. Yeah, 1100 is 10, so this is 11. That makes sense. Okay. So no, that doesn't make sense. I've got it backwards. 1011. Okay. That makes sense. Okay, so 1011. But I said I wanted 7 and I got 4. I'm going to make those. I had to add in by hand because I asked for 7 and I only got 4. And so I needed some leading zeros. Up here in the whole number, I threw away the leading zeros. I don't want them. I'm doing floating point notation. I'm interested in it starting with a 1. So I don't want any damn leading zeros in my whole number. In my fraction, I might need them. Now, what was my fraction? My fraction was 0.09. The first place is a half. That was less than a half, so that makes sense. The next was a quarter. The 0.091 is less than a quarter, so that makes sense. and the next one is an eighth, and that's 0.125, and this is less than 0.125, and so that was a 0. And then this is the 16th place, which is 0.0625 or something, I don't know. And that, so that makes sense. So that I'm more than a 16th, I'm less than a half, less than a quarter, less than an eighth, but more than a 16th. Okay. So now I have my 17 and my 7, so I have my 24 bits. So at this stage, here's what I'm thinking I have. Copy, Control V, and then the dot, and then this. So this is what I have at this stage. Now, what is my rule? My rule is to move that dot so that it's the first non-zero digit and then the dot. So my rule is to move this how many places? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Is that right? Yes, 16. One less than this. Okay, so to play my game, I need to move the dot 16 places. I am making the number in front smaller by moving the dot. So I compensate that by multiplying by positive powers of 2 to compensate. I'm making the front number smaller, so I got to make the power of 2 bigger. And so what do I end up with? I'm going to take this. I'm going to have here. I'm going to have a dot here. Get rid of the dot there. And then to compensate, I'm going to multiply by 2 raised to the, what did I say, 16. I moved the dot 16 places. Okay, almost done. The 16 needs to be biased. So bias the 16, bias the power. So that is 127 plus 16. And I'm not going to be the hero. I'm just going to add. So in decimal, 127 plus 16 is, that's crazy. 127 plus 16 is 143. That seems to make some sense. And that in binary, because this is a binary representation, is down here. Control V, there we go. Okay, so I have, that's my exponent. This is almost my mantissa, except what? I have to, now is my time. I'm ready to store, I'm ready to give my final answer. And so my mantissa, what the hell am I doing? So I'm going to take this and I'm going to take this away. I'm done with these. And take the 1 away. And I'll have my mantissa. Take the first 1 away. Okay. So my sign bit was a 1, easy enough. My exponent was this guy, the biased power. And my mantissa is these 23. I was working with 24, but that first very 1 is always 1. And so I don't store it. Okay. So now I'm going to check my answer. So I'm going to say floating point calculator Schmidt. That's the calculator I like. And I'm going to put this in. Now I'm showing you here there's calculators, and I'm letting you also know that there are other calculators. And so what am I going to put on the test? For full credit, you're going to have to provide me a bunch of intermediate steps, so you're not going to get credit. It's definitely a show your work problem. If you want to write it on a piece of paper and take a picture of that piece of paper, that's fine by me, but I need some kind of work, not that you're just using a floating point calculator and that's that. Okay. So what was my sign bit? It was a 1. What was my power? Where was my power? Here was my biased power. 1,000,1111. 1,000,000. There were 4 O's, right? No, 3 O's and then 4 ones. 3 O's, 4 ones. There we go. Okay, and you see the number starting to get in the right ballpark. It was a negative number. I'm up to 65,000. So I'm not quite to 90,000, but I'm getting there. Okay, now let's play the Mantissa game. I'm not going to represent that 1, that's implied, but I'm not going to show it. And let me get that a little bit higher so I can see them both at the same time. And so what I'm going to store, it's a 0, then 1, 1, and then 3 O's, and then 2 1s, and then 0, 1, 1. Now I'm 1, 1, 1, 1, another 1, 1. So it was 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1. Then 1, 2, 3, 4, 5 zeros and a 1. 1, 2, 3, 4, 5 zeros and a 1. And then a 0 and 2 1s. Okay. So I have minus 90988.085. So I'm not getting quite my number, but that makes sense. I can't represent these fractions exactly. There's always going to be some rounding in this game. Okay. So let's play the game in reverse, but let me ask if there are questions. So there are 3 games, and I probably only have time to play 2 of them. One is take a number which is greater than 1 and represent it. And then there's the game where we take the number that's less than 1. Doesn't matter whether the number is positive or negative. So when I'm talking about bigger or smaller than 1, I'm talking about its magnitude, not its sign. The sign is trivial. It's the sign bit. 0 for positive, 1 for negative. So I'm talking about like the magnitude, the absolute value of the number. So if the number's bigger than 1, that's the game we just played. There's a game where the number is less than 1. So then you're like shifting in the other direction. And then there's the game of I give you some representation in a floating point numbers. I give you the 1s and the 0s, and then I ask you to come up with a number. So does anybody care which one? I have 2 more to go. I probably will only have time for 1. Does anybody care which one I do next? She says no. Nobody's shouting at me. So I will do the float, the 1s and 0s, and get to the decimal. I have an example. You remember, of course, that I have these posted slideshows. These sessions are recorded and posted, but I also have some pre-recorded stuff. And I do have in there a number that's less than 1 for people who are anxious to get moving on the labs. That would be lab 7. Okay. So let me give you, so I'm going to save that. So that we were done that. So let me insert a page break and now play a game. Let's say the sign bit is a 0. The exponent is, I don't know, 0011 1100. I'm just making crap up, who cares? Okay. And then the mantissa is, what is that, 23. So I'm going to say 110, 110, that's 6, 110, 110, 11. How many? So I should have made a 4-thing pattern. So here's 4, 8, 12, 16. So that's 1, 2, 3, 4, 5, 6. So that's 24. So that's too many, right? So it's 23 like that. Okay. 1, 2, 3, 4, 5, which is 20 because it's groups of 4 and 3 more. Okay, so that's the mantissa. So now let's play our game. So first thing you do is you say it's an overall positive number. Okay, that's easy. Then I'm going to come and deal with the exponent next. Let me put this all below. So that was the problem, and then I'm going to tell you bit by bit the answer. Overall positive. Okay. So the number will be positive when we're done. Some people, I just remember like 0 is for positives and 1 is for negatives. Some people will take -1 and raise it to the sign bit. And so if you take, if you raise something, anything to the 0 power other than 0, that's weird. But 0, yeah. So if you take anything and you raise it to the 0 power, you get 1. And then if you take -1 and raise it to the 1, you get -1. Anything you raise to the 1 power, you get the thing. So I just remember, I just do it as a memory thing. 0 is positive and 1 is negative, but some people will do that -1 raised to the sign bit thing. So if you poke around, you'll see somebody who does it. If you like that, fine. If you just want to remember, fine. I don't care. It's you know, some people think, my way is confusing. Some people find the other way confusing. So it's sort of, whatever works for you, do it. Okay, let's do the exponent. How did we get to our exponent above? It was a power of 2, and then we biased it. So now we have that result. And so we are going to, I call it unbias it. So I'm going to take this exponent. I'm going to put it into a decimal. And then I'm going to unbias it. So I start here, Control V, that is my exponent. So I'm going to put it in binary mode. I'm going to clear out. It's going to be 0011 1100. So there it is. It doesn't show me up here the leading zeros, but I did, they are there. And then I'm going to say, what is that in decimal? Oh, that's 60. And then I need to unbias it. So if bias means add 127, unbias means subtract 127. And that's minus 67. That makes sense. And so that's my power of 2. When it comes to the end, I'm going to multiply by 2 raised to the minus 67. Okay. Now let me deal with the mantissa. And again, different people do this in slightly different ways. You can bring the 1, remember we took away a 1. We can take it away. We can bring it back right away, or we can bring it back later on, depending on your taste. Okay. I think I'll bring it back right away. But if, there's another approach where so I'm going to put the 1 back in. And so this is what I'm thinking I have at this stage. Okay, so I'm thinking I have 1.110, yada, yada, yada. And if I were a glutton for punishment, I could start saying, okay, this is a 1, and then this is the halves place, and this is the quarters place. There are no 8ths, there's a 16th. I can start to sort of pick out what this number is, but let me play the following game. The dot is a problem. I prefer whole numbers. Whole numbers, my calculator, I'm a cheater, I like the calculator, and the calculator understands whole numbers. So let me make it a problem of whole numbers. To make it a problem of whole numbers, I got to move this guy 23 places. So if I move that guy 23 places, I've got to compensate for that. And so here's my game. Just sort of the opposite game that we played before. I'm going to move the dot 23 places, making that small number a big number. And so then I compensate by 2 to the 23. That's the same, right? That's the same game we played before, just in reverse. So before I made the number, I had a big number and I made it small, and then I had some power of 2. Now I'm making the small number big, and I'm dividing by a power of 2 to the 23. Same game. Now I made this number big, and so then I divide by this, or if you want, you could say it's times 2 to the minus 23. That's another way of saying it. Okay. But now I have a bit string that's all 1s and 0s. Let's see if I can copy and paste that into my calculator, or do I have to retype it? I'm going to be in binary mode. I'm going to clear. I'm going to be in binary mode. If I paste, you put it in. Okay, just ignored my little spaces. And that's good. And this is, it gives me this thing called digit grouping, which is groups of 4. If for some reason you don't have digit grouping, it's maybe it used to be a choice where you could have it or not have it. So somewhere it's a choice, but it chose it for me and I like it, so I'm going to stick with it. It's got 1, 2, 3, 4, 5, 6 groups of 4, which is 24, and that's right for me because I brought that 1 back. And here's the decimal number. So now I'm going to copy that, and this thing becomes, I take my bit string and I put it into decimal, and I divide that by 2 to the 23. And so that is what I have to do next. So I'm going to move my calculator. You can do some of this like in Google. Google, if it can be a calculator. But I'm going to take this number, copy it, copy. Control C is copy, right? Control C. Go over to programmer mode, and no, not programmer mode, scientific mode, and paste it in there. And then I'm going to divide by 2 raised to the 23. and I get 1.8. I get this big crazy thing. Okay. That makes sense to me. I hope it makes sense to you. Remember that the mantissa was bigger than 1, and then it was 1 plus a half, so it's bigger than 1.5. It's bigger, it also has a quarter in there, so it's bigger than 1.75. And so now I put the pieces together. It's positive. The overall number was positive. Then I'm going to take the number from my mantissa, Control V, and I'm going to multiply that by 2 raised to a power, which was minus 67. Okay, so I still have in my calculator, I still have the one, yada, yada, yada. I'm going to multiply by 2 to the 67, or if I want, I can divide by 2 to the 67 if you prefer positive powers. I'm going to try and multiply by 2 raised to the 67 and do a plus minus. And so there's my number times 2 to the minus 67 equals. And then I get some tiny number. And that is my, and remember, E is the sort of computer's notation for scientific notation. So this E is really times 10 to the minus 20. So the answer is 1.258 yada, yada, yada times 10 to the minus 20. All right, let me see what Herr Schmidt has to say, and then we'll call it a day. So here is the Schmidt calculator. What does he have to say? Let's refresh it. It's 0, it was 1, 1, 1, 1, and then it was 1, 1, 0, 1, and it was just 1, 1, 0, 1 on down the line. So I tried to make it easy for myself to enter in this calculator. Sometimes I'm nice to myself, sometimes I'm nice to you. Okay. And they say the answer is 1.2844 times 10 to the minus 20. Okay. Can you just use the calculator? No, not if you want full credit on the lab, not if you want full credit on the exam. Okay, I'm going to quit there. I'm gonna stop recording, I'm gonna share and check my attendance.